JIGYASA Grover from San Francisco. She's a machine learning engineer at Twitter, and besides being a data scientist, she's also an open source enthusiast. And more interestingly for me, she was also heavily involved with bridging the gender gap for women in technology. She was director of Women Who Code and lead of Google Women Tech Makers. So after all these interesting things we heard you or know you about, Jigyasha, please continue with your presentation.
Sure. Thanks, Rolta, for the nice introduction. Hey, everyone. I am JIGYASA Grover, and I hope everyone's having a great time today. Today, we'll be talking about how we can fuel our machine learning models via feature engineering. So the last couple of years have seen an immense growth of machine learning in multiple domains, from influencing our shopping lists to cars self-driving around the town. Unquestionably, machine learning is the most used and abused subdomain of artificial intelligence presently. It is being wielded in improving healthcare, advancing warfare, scrutinizing your resume to determine your creditworthiness, in creating music with meaningful lyrics, to synthesizing pictures and videos of even non-existential people. Regardless of our fascination or loathe for it, it is influencing decision-making power and is dominating our lives heavily. To describe, enabling computers to learn on their own is what encompasses machine learning. The power of spotting patterns on their own without the requirement of programming is the biggest edge these decision-making systems have over the others. Researchers keep traversing the unexplored territories of machine learning, whereas according to experts, the business have just seen the tip of the algorithmic iceberg. According to Finances Online, $28.5 billion were allocated to machine learning worldwide just in the first quarter of 2019. And it is expected to grow up to $40 billion by 2025. And we had started from just $1.3 million in 2016. So we've come a long way from there. And almost 50% of the companies either have started exploring or planning to do machine learning in the near future. Even the number of startups based on machine learning services are having a 14 times increase currently. And 97% of mobile users use machine learning trained voice assistants for search now, and with 40% of search powered by voice. So we can definitely say that dominant leaps are leaving the scientists, investors, policymakers, business leaders, and the audience, all bedazzled, hinting like that human-like intelligence in machines might be just around the corner. Nonetheless, progress in machine learning has been impressive, but there is a lot of pending explanation and examination which keeps the research going on. For the state-of-the-art learning algorithms to work their magic on, it is important to focus on the three key dimensions: well-calibrated data, sophisticated algorithms, and efficient computation. So these are the three key dimensions one needs to focus on for the state-of-the-art machine learning algorithms to show their magic. When we talk about these three things, you can say that the strong build of learning algorithms comes from the iterative process of validating hypotheses via experimentation. Whereas efficient computation comes through optimizing the learning algorithm using distributed computing to run at a large scale. However, laying the foundation of the process with perfect quality and the perfect quantity of data is the secret sauce for creating a successful machine learning model. Since we have progressed from the rule-based approach to more a data-based approach, it goes without saying that machine learning algorithms are as good as the data that they get. Hence, it is very true to say that these approaches, especially the ones like neural networks, they're very data hungry. So in this sense, having a lot of data is the key to come up with good training sets. However, feeding the right format of data also matters. Worthy data collection forms the foundation of the pyramid of the AI hierarchy of needs, which is drawn parallel to Maslow's hierarchy of needs by Monica Rogati, who is a renowned data scientist and an AI advisor. She puts forward that data literacy, data collection, data flow, form the basic needs which must be satisfied to achieve self-actualization or nirvana, which in our case would be the ultimate attainment of AI. Hence, this basically puts forward that even though machine learning is not magic, it's just algorithms that work in their own way. And the foundation is laid by the algorithm, the computation power that we have, and the data. But also in data, we need to have the perfect quality and as well as the perfect quantity of data. So there might be a few additional steps in the pipeline before we can use the data that we have to train a machine learning model. These values are basically understandable easily by humans. The values are the data values basically. But machine learning algorithm might have trouble learning from the type of data, and it might just need some more encoding or embedding that needs to be done. Let us just consider this simple image of yin and yang. Its dimensions are, say, 350 by 350. For us, it is super easy to understand and associate it with something. But for a machine to understand, what we need to do is kind of like a vectorization. This mandatory transformation involves converting all kinds of non-numeric data, be it textual data, graphical data, categorical data, any data which is kind of like in a sequence or non-sequence, to turn into more of like a numeric form, or say into numbers, which are only what a learning algorithm can comprehend. So something like this, we could transform into something like this. So maybe like the color of each pixel could be translated into like a number. And learning algorithms require graphical data such like this to be an input of numbers, matrix of numbers per se, like the JPG, PNG images, they can be loaded as array of images. Hence, for a grayscale image, this could be a 2D array and so on, depending on the kind of image you have. So in short, the process of transforming raw data to a set of quantifiable values is called feature engineering. Um, a feature, you could say, is an attribute or property shared by all of the independent units on which prediction is to be done. So first you transform the data, the image, into like a vector of arrays, and then you create features out of it. And that's what is called feature engineering. So feature engineering is one of the key techniques that often does not get it due limelight, be it academia or industry. And much of the success of machine learning is actually success in engineering the features that a learner can understand. Um, you can say this is where your intuition comes into play. This is where you can play along with creativity. And most of the times, this step is much more important than the actual modeling process because, as we said, machine learning model only learns from the data we get. Hence, it is necessary to spend a considerable amount of time engineering features for our model to consume. You can say that choosing the right features in the right format can boost your even simple ML models by a lot. It, it is just dependent on a simple theory of garbage in, garbage out. So by using good features, great features, you not only increase the transparency of the model, but you can also boost the performance. And you can reduce the need to use heavy ensemble learning techniques. You reduce the need to use like complex techniques, and it also reduces the need for tuning hyperparameters often for their optimization. So all these things help for machine learning to grow, to fuel. But it is also necessary to know like what is the process that goes behind feature engineering. Um, as we say, this step is actually more important than the actual model we used. So it's necessary that we start with analyzing trends, researching domain, and coming up with a feature idea. We discuss with people and brainstorm, especially in the same domain, machine learning engineers, data scientists, and so on. Before we jump right ahead, we do like a quick offline transformation and perform statistical analysis, whether the potential feature is having enough data, what is the distribution of it, and so on. And then usually in a formal setting, we test it in an existing offline setting and not going into production directly. If it doesn't work in the offline setting, we go to brainstorming all over again and try improving it. We work on getting it productionized, integrated in online pipeline, and so on. So this is how the iterative process of feature engineering is. You start by researching your domain, analyzing trends, and step by step perform statistical analysis, offline experimentation, and online experimentation. So this is usually how like a formal setup is done. And definitely coming up with features is very difficult. And Adrian G said, it is time consuming and requires expert knowledge. You usually build on it. And feature engineering is again applied machine learning in itself. But it is also necessary when you're doing feature engineering to understand what are the non-goals of feature engineering, because usually many times people include a lot of things in feature engineering which might not actually be a part of it. So let's say the initial data scraping or collection does not form feature engineering. Recognizing the target variable or performing statistical analysis on it does not form feature engineering. Scaling, normalization, any part of data transformation or data cleaning, including removing duplicates, handling missing values, imputation, etc., do not form the part of feature engineering. Hence, now that we've talked about the importance of features, it is good to know, like for a comparison, let's say if data is the crude oil, features are the fuel we need. And we should also be talking about the extraction process or techniques of feature engineering. So let us just quickly go through the different techniques that we need for that extraction process. Imagine that you have like an app store preview page. You extract like basic information for it if you wanna like say recommend an app, you're building like an app recommender system. So you would have data like App Store, iOS App Store. The category would be like a social app. You have languages like English, Hindi, French. Then the app age days would be how old is the app, would be like 1350. And then we have like app rating, which is 4.7. To use these app recommender systems input as features, you would have to like do transformation on it, because this is clearly data and this is not feature. To create like feature out of it so that like into a numerical purpose so that a machine can understand, you could do something like encoding. So for the App Store, it is available in iOS App Store, out of Google Play Store, and like you could even keep buffer in your array. So you just did like 1000, or in this case, it should rather have been 0100. Then the app category, you have like multiple categories. You could again do like multi-hot encoding if the app belongs to multiple categories. Same goes for app languages. It could be available in different languages. So you could be like multi-hot encoding, as in you have an array and like you have multiple places going on. But app age stays, since it's numerical, you could keep as it is. It is not like a categorical feature. Same goes for app rating. It's like a continuous feature. You could have rating anywhere between 0 to 5. So this is how you did like the basic transformation. And now they are ready to be used as features for your app recommender system. Of course, when we are trying to build like features out of a data, it is easy to go haywire and you could like create multiple features. But does that make them worthwhile to input into the feature, into the model? Like, how do you know which maximum signal they give, and what actually constitute a good feature is also necessary to know while you're doing feature engineering. So let us just talk about like what makes a feature a worthwhile feature. So the first would be avoid discrete, rarely used discrete features. So a feature that appears like say less than 5 or so times, you could have a threshold, is not a good feature. It should have like enough differentiating power. Minority instead leads to a point where like majority gets overshadowed. Sorry, majority overshadows the minority and becomes anomalies instead. You should also prefer clear and obvious meanings for the feature name itself. For example, we used app age previously. It might be confusing because for someone who's new to the model, understanding like, is it in days, years, months, etc. So like having a name which says app age days is more clear and meaningful. The second would be avoiding value discontinuities. We all know that for an app rating, the values would lie anywhere between 0 to 5. So for having a value sometimes as -1 is kind of like an out of range value. So you could mark these like explicit values using like is app age defined, like introduce a new feature for it. This is one way you could make sure like the feature you have is worthy. And the second would be, let's say you had like an app language, say English. Instead of like directly using like an external mapping, English to say 24, it is important that you do encoding or embedding inside the feature engineering process itself, because many times it could be possible that the mapping of English or say languages to different numbers could change in the external mapping, and it could harm your model in the long run. So these are the ways. And while we talk about it, we said like it is easy to go all over the place and bring in like too many features. This is what is called like curse of dimensionality. You could have too many features because of encoding, embedding, and that's when it just bloats up the feature space. um, Observations become harder to cluster because the more number of data, and it just requires more data to generalize accurately. It also causes like every observation or like every data point to appear equidistant from all others, leading to a like a much harder problem and poor performance. And this is what eventually leads to a quick growth in the total number of features, known as feature explosion. Because you bloat up the feature space, there's just too much going on. And this is where you need to stop using techniques like regularization, kernel methods, and feature selection. So talking about feature selection, it would be the process of selecting a subset of relevant features for use in a model construction is basically what encompasses feature selection. You should be, it is aimed at making predicted variable more accurate, and eliminating irrelevant attributes. So irrelevant attributes could be like irrelevant features which like are present in the model but do not contribute enough signal, or sometimes there are features which are like correlated to each other, which we like talk about later. So all in all, feature selection leads to simplification of models. You're basically choosing like a subset of features which are like most significant for your model. It makes them easier to interpret because you know which tuning which feature, or like removing and adding which feature is leading to gain or not. It helps in shorter training time because you know the hashing space is less. It protects you from the curse of dimensionality, and in general reduces overfitting. But while you're doing feature selection, it is also necessary to have like a list of rankings, say like, how do you know which feature is more important? Because not all features assist the model in the same manner. Let's say we had like 100 features to begin with. Feature selection led us to top 50 features. And how did you select top 50 features? One of the methods could be feature importance. This is where it comes into play. You could understand to select the subset, or just to explain the predictive power of the features already present in the training data set. It forms a critical part of ML interpretability and explainability. One of the common techniques to compute feature importance is via, say, randomized decision trees. So what it does is it averages the predictive ability of a feature over several randomized trees, and one can reduce the variance of such an estimate using, and thus use it for feature selection. So basically, you compute the predictive ability over different trees and then average the estimate. This method returns an array of feature importances for each of the feature, which total add up to one for a particular model. And let's say we did the same for app recommender system. It would be, let's say these were our feature importance scores. So it is necessary to know, like for this method, higher the score, more important the feature. So we can understand that app languages is much more important feature than app category. It's very necessary to like plot this out for your own understandability. And in the same case, we all know like relationships matter, and it holds for machine learning features as well. Um, let's just study this graph carefully, and we can come back to it like understanding what it really means. So in this graph, it says like when the app price goes down, you can see the purple line. The green line is going up, kind of like, which is the app rating. But when you see like the app languages are plotted, like the number of languages, it just doesn't have like kind of like correlation. Um, so this is just like a random, like say the number of app installs are increasing as the app price is going down. The number of app installs is increasing as the app rating goes high. So which is kind of like an obvious indication to us. But like it becomes necessary to understand such relationships between multiple attributes and in the data set. And this is what is called like feature correlation, how you can correlate the relationship between multiple attributes. It leads to useful insights like one or more multiple attributes could depend on other attribute or cause another. Correlation can also help in predicting the other attribute. Let's say I had a feature A and feature B. A feature B had some missing values, but I soon realized that feature A and feature B are correlated. So I could basically impute those missing values using the values of feature A. It is a great way to impute or say fill in missing values. Correlation can also sometimes indicate the presence of like a causal relationship, but it is used as a basic quantity for many modeling techniques. So now let's come back to that graph that we were talking about. You can see that the number of app installs, which is on the x-axis, is increasing as the app price is going down. So we can say like they're going in the opposite directions. So we can say that they're negatively correlated. Whereas if you talk about app rating, the number of app installs are increasing as the app rating is increasing. So they're increasing, they're both going in the similar direction. So we can say they are both positively correlated. Whereas you talk about app languages, there doesn't seem to be like any direct relationship between number of app installs and the number of app languages. So you can say they don't have like any correlation as such. So all in all, correlation can be like thought into like three different categories: positive, negative, no correlation. So these are how you can judge like if the features move in tandem or not. And they become very important, especially when you have to like remove features or add features or just have like a short on feature space. As you must have comprehended by now, feature engineering is definitely an exhaustive process. Data scientists and machine learning engineers often don't find this data messaging and feature engineering job to be as exciting as machine learning modeling. And typically, feature engineering is a drawn out manual process, relying on domain knowledge, intuition, data manipulation, and it's very time consuming. It is extremely tedious, and the final features, ultimately the set that we have, they can be limited both by human subjectivity and time. Um, this is where like feature automation comes into play because it aims to help the data scientists and machine learning engineers automatically create candidate features or a list of potential features out of a data set, and from which we can select the best using these techniques that we have talked about: feature selection, feature importance, and correlation, and so on. One of the tools that is often used is like an open source Python framework called Feature Tools. And as Pedro Domingo says, one of the holy grails of machine learning is to automate more and more of the feature engineering process. Because good and reliable feature engineering is like laying a strong foundation for machine learning modeling. And it is also important to note that more data can beat your clever algorithms, but better data always beats more data. With this, I would also like to basically route you to the fact that if we have like a workflow like this, majority people focus on defining the metrics of success for an intelligent solution and choosing the appropriate model. Like this part of the ML workflow is what majority people have been focusing on. And it's very necessary that we focus on this part of the machine learning workflow, which is sourcing the data, fabricating your own data set, processing the data set, and performing feature engineering. This is what would form the core of it. And just recently, like a month ago, me and my co-author launched a book on it, which is also known as Sculpting Data for ML. It introduces the readers to the first act of machine learning. In case you're interested, this is the link. I'll also leave the link in my slides. what's inside. You could find different ways to basically sculpt your data, identify relevant data signals, end-to-end process of data collection and data set curation. It's basically a step-in-step guide by Python. It is endorsed by leading machine learning experts, Julian McCauley from UC San Diego, Lawrence Verney from Google, and Mengting Wang from Microsoft. Thank you so much, everyone. It was a pleasure to meet you and hope you're having a fun time. Let me know if you have any questions.
Thank you, Jigyasha. It was really interesting. As you wrote in your abstract, this is a really innovative part of data science. Yes, and we do have questions. But before we go into the questions, let me remind you that the poll function can be used to use the to rate the talk and give some feedback to the presenter. And then the questions. Can you elaborate how the feature engineering increases transparency?
Yeah, for sure. Feature engineering is basically if you have like a subset of features, which you know are very important, especially like feature importance. It would increase the transparency in the sense that you would know which signal, which feature is giving like how much signal to the model, and just explains the transparency and understandability. Of course, the techniques in neural networks like neural additive models and variable importance via neural networks, which helps you like map out the exact process of like which feature is giving how much signal, and that in my opinion would increase the transparency of the model.
Thank you. Another question more from this tech leaders and women point of view. So how do you see the place of women in AI and, for instance, in feature engineering?
Yeah, for sure. So I can definitely talk about it. Currently at my workplace, I am the only female in my team, and it does get a lot of honestly, though it is a very nice work culture and I'm enjoying it just takes an extra effort from our end to put ourselves out there and ask questions, because sometimes it is very easy to like think like people know everything and you might not, you will be the only one who does not. So asking questions, definitely, it's okay to ask questions. That is something that I would always encourage, even though how stupid they might sound. That is how you will increase your own understanding and grow in this field.
Thank you. Another question on the talk. Could you give some examples on what can be automated?
So definitely. So as I talked about, the automation was using feature tools. Is basically you give it a complete data set, and the tool would give you like a list of all the potential features. Because as we talk about, feature engineering is highly limited by our domain knowledge and by the modeler itself. So it's very necessary to have like a potential list of features, and from there you could run methods like feature selection, feature importance, and then choose like a subset. So in that way it would be like easier for you not to like go through the entire list, and as I said, like it is limited by domain knowledge.